recording. To introduce our speaker today, this is Asen Dontchev from University of Michigan, a great friend and a great mathematician. So I'm very honored that he accepted our invitation. So Asen Dontchev he was born in Bulgaria, and he received his PhD in mathematics in Poland. And after that, he was, so this is a very, very nice history and a story. After that, he was a professor in Sofia at the Academy of Sciences, and for a long time. And in the 90s, he moved to the US. He was affiliated with the American Math Society, where he was an editor for the math reviews. He was affiliated with the University of Michigan, and he's currently affiliated with the University of Florida. He's one of the great mathematicians we have in optimization and analysis, with a very broad profile, with amazing contributions. And I would just like to mention a beautiful book he wrote together with Terry Rockefeller. And I like to tell you a secret, namely that, am I allowed to say this? That a further book
Sure, go ahead.
In preparation now. Okay, so thank you for accepting our invitation, Asen. It's nice to have you here. You have 45 minutes for a talk.
Thank you very much. Thank you very much to you, Radu, and all the organizers and other organizers for inviting me and to giving this opportunity. This is a privilege for me, honor. So I'll try my best. I'll be talking about sensitivity analysis without derivatives, and I immediately would like to mention that I plagiarized. I plagiarized the title from the book of Jean-Paul Penot, which actually is a very nice book, and I would recommend it to everybody who is interested in generalized derivatives. But it's not true that in the book there are no derivatives. In this book there are no derivatives. It's full of derivatives, but they're not the usual one. They're generalized derivatives. But anyway, I'm not going to be talking about generalized derivatives in this talk. And here is the outline of the talk. It will start with some historical facts and results. And then we go into applications, and the main application will be in optimal control. Here is the outline of the talk. I'm not going to read it here. The main focus will be on strong regularity, and then the applications of strong regularity to nonlinear programming and optimal control. So what is sensitivity analysis? Generally, it is understood as estimating the effects of changes of a problem on solution. So we change the problem, we make some perturbations of parameters there, or there are some approximations performed. Any of those changes of the models affect the solution, and the sensitivity analysis is basically how estimating the effect of these changes on the solution. It has been traditionally identified with determining the derivatives of the optimal value and optimal solution with respect to parameters, and this is quite natural because the derivatives, they're measuring the sensitivity the rate of changes. But in optimization problems with constraints, finding the derivatives may be very challenging. And then that's why generalized derivatives were invented. But the generalized derivatives mostly work in finite dimensional problems. When we talk about optimal control, when we'd like to do sensitivity analysis in optimal control, there are even more challenges. Namely, we have to differentiate in infinite dimensional spaces, which is quite a difficult task sometimes. Okay, let me start from the very beginning. Okay, maybe not the very beginning, but this is what I know that the first sensitivity analysis result, which kind of states like a classics in mathematical programming and nonlinear programming, is in the book of Yaqua McCormick, which is cited here. I should immediately mention that sensitivity analysis in this book was not the central topic. Basically, the numerical analysis of optimization problems were the central topic, and the sensitivity analysis was used as a tool for proving convergence of algorithms in this book. So let me, I would like to present now the main theorem about sensitivity in this book. And it's I put it in the framework of nonlinear programming with inequality constraints. I didn't put the equality for simplicity. So we introduced the Lagrange function in the usual way, and under constraint classification, we can write down the KKT conditions, the optimality conditions for this problem. I'm not going to write it down here. I'll write it down later. And here is the theorem, which is linked with the names of Yaqua, Tony Yaqua, and Garrett McCormick from the 60s. Okay, so suppose that X bar is a solution for P bar. P bar is the parameter, and P bar is the reference value of the parameter. And suppose that Y bar is the associated Lagrange multiplier. And then we have three conditions here. The first one is that the gradients of the active constraints are linearly independent, which is very common condition in sensitivity analysis. Then the second are the sufficient condition holds, which is also something that might be expected. And the third one is the strict complementarity slackness condition. Then if this three condition holds, the mapping from P, acting from P to the set of solutions plus coupled with the Lagrange multiplier has a continuously differentiable single valued graphical localization around P bar for X bar, Y bar. Okay, please remember now, when I'm using this continuously single valued graphical localization, when I'm using this concept graphical localization, I mean the following, that you have a mapping, you have the graph of the mapping, and then we take a particular point in the graph and we make a neighborhood of this point, and then forget about everything outside this neighborhood, just consider what's happening in the neighborhood. And if in this neighborhood, the mapping looks like a function, then we talk about, it's single valued, then we talk about graphical localization of this mapping. So single valued graphical localization. It might be not single valued, of course. And then we add to that the function which identifies the graphical localization has some properties. And in this case, this graphical localization is continually differentiable around the reference point. Out of these three conditions, the third condition is most troublesome, most kind of difficult, because it means that the Lagrange multipliers, the value of the Lagrange multiplier corresponding to active constraints, this means that when these G's are equal to 0, must be positive. But this condition is never satisfied at points where the constraint change from active to non-active or on the opposite direction. So here is a little picture I try to make. So here is the value of the constraints G. It's negative here, and then it's 0, and then the value of the Lagrange multiplier is 0 here, and then it's positive. So at this point, if these functions are continuous, there's no way that the strict complementarity slackness will be satisfied. And this is this is even worse in case when you have optimal control, where Well, we have variables that are continuous. Say the states is a continuous function of time. Time is the parameter now. And we have constraints in the state or in the control. Control also could be continuous. And in that case, in order to apply this theorem, we have to assume that the constraint never change from non-active to active and back, which is nonsense, of course, if we have a constraint optimal control problem where the constraints, if they're non-active, they're just non-existing. So, this theorem cannot be applied in this particular case. Moreover, in the points where we have change in the constraint, the solution is usually non-differentiable. So we have additional complication here. We not only can we apply this theorem here, but also we cannot apply any theorem which gives us differentiability of the solution because it's just not differentiable. So what to do in this case? Well, we have to look at non-smooth analysis and try to figure out what kind of fact, what kind of theorem we would like to use in order to study this case. Well, in this work, Fiacco and McCormick, as well known, use the classical implicit function theorem, because under these three conditions, in particular this third one, the trig complementarity slackness, the optimality system reduces to just a system of equations. And to this system of equations, we can apply the classical theorem. But now we don't have this situation. So we have to apply something like a non-smooth implicit function theorem. And where to look for non-smooth function implicit function theorem? Well, this is something which started in the late 70s. People start talking about this, but the first non-smooth implicit function theorem appeared much earlier. It appeared in 1927. And this is in the work of Ted Hildebrand and Lawrence Graves. A paper, very important paper, in my opinion, which is published in a Transaction of IMS in 1927. And this is the theorem here. The paper is very interesting to read. It was written several years after Banach thesis, and half of the paper is devoted to introduction of Banach spaces, which the authors don't call Banach spaces. They only call them B spaces, and then they are F spaces, and then they mention in a footnote that Frechet called them Banach spaces, but not them. Anyway, so here's the theorem. We have a Banach space X. Of course, I'm updating this theorem, the statement to today's notation and terminology. We have a Banach space. We have a function acting from X to itself. And also we have a linear bounded mapping, which is also acting from X to X, which is invertible. I mean, the inverse is linear bounded. And also we make the following main assumption, and the only assumption here, that the Lipschitz modulus of the difference between F and A, between the function and the linear operator A, at the point X bar, times the norm of the inverse of the operator A is less than 1. And the conclusion, so what is the Lipschitz modulus? So here's the definition of the Lipschitz modulus. This is something quite standard nowadays. This is just the lim sup of this ratio here, which is basically something which is a bound from below of all Lipschitz constants of this function. Okay, so if this condition holds, then the inverse of F has the conclusion is it has a single valued localization, which is Lipschitz continuous. And this is 1927. Okay, they're not talking about derivatives here. Well, you may guess that this less than 1 means something that there will be a mapping which is contracting, which is and they will apply the contracting mapping principle. Indeed, they do apply this principle, and they cite Banach for that. Although this principle has been known before Banach, probably, most likely. So this is a theorem where we are talking about the existence of a single variabilization of the inverse of a function without mentioning any derivative. Of course, if A is the strict derivative of f at x bar, which means that this Lipschitz modulus here will be 0, then this condition will be automatically satisfied. And we get the classical Dini inverse function theorem. F is strictly differentiable, and then we have that the derivative is invertible, then the inverse has a single variable localization. We didn't get from here that this localization is continuously differentiable, but when we know that it's Lipschitz continuous, proving that it's continuously differentiable is really very easy. So we get it for free, basically. So here is the Hildebrand-Grace theorem. And here are the pictures of Hildebrand and Grace. Few words about both of them. Lawrence-Gracie is the same Lawrence-Gracie of Lusternik-Grace theorem, Bartók-Grace theorem, great mathematician, analyst, who basically introduced functional analysis to the United States. Also, he worked all his life in calculus of variations. And he is also spent all his life in Chicago. And also a less known fact is that he was the supervisor of Karush, the same Karush who is now in the Karush to Kuhn-Tucker condition. He was the supervisor of the master thesis of Karush, where the Karush-Kuhn-Tucker theorem was stated for the first time. Well, it's very highly possible that he knew about this theorem before Karush. Sorry about that. Okay, and it's really an interesting detail. Also, he was contemporary of the birth of optimal control, and he did a lot of calculus of variation with constraints, but you know, the optimal control went by. He didn't notice it. He didn't. I don't know, not notice, but he didn't work on it. Very interesting. Ted Hildebrand was spent all his life basically in Michigan, and they worked together quite a lot. And he's been chairman in the math department of the Michigan, and also president of the American Mathematical Society for a long time. And now there is a scholarship in his name in Michigan. So it's a pleasure to mention him here. Okay, so the breakthrough to fix this strict complementarity slackness in the Fiacco-McCormick theorem came from a very different direction. It came from Steve Robinson, who in the 1980 published a paper, which is about the implicit function theorem, but not for an equation, but for a variation inequality involving a function depending on a parameter, and also a set-valued mapping. And now we are talking not about the equation, but about the inclusion. So it was a completely new idea in the whole history of implicit functions, not to consider equations, but to consider inclusions, and still obtain a statement about the dependence of the solution of this inclusion on the parameter. And this was in 1980. And Steve Robinson had in mind optimization, of course, in this in his paper, and he applied his theorem to an optimization problem, mathematical programming problem. Yeah, this was really a very new idea to consider inclusions, not to consider equations. And why should we consider equations? So we can consider inclusions, we can consider minimization problems as problems defining implicit functions. Why should they be only equations? So this was a very revolutionary idea. And what Robinson had in mind is to apply this to variation inequalities. And he actually considered the inclusion of this particular case, where the n is defined as the usual normal column mapping to a convexly closed set C, which is assumed for the set C. And this is defined right here. So if we apply this definition to this inclusion, we'll get the usual statement of a variation inequality. So what the Robinson theorem says, in a simplified form, it says that if we take the linearization of this sum of a function plus set valued mapping and C, meaning that we linearize just the function. Of course, we have to assume that the function is nicely differentiable around the reference point. If we take the linearization plus the normal column mapping, which is the same as taking the linearized variation inequality, and if this linearized variation inequality has a solution, which in this case will be the inverse, which depending on the right-hand side, has a solution which has a desired property of having Lipschitz continuous single-valued localization, then the solution mapping of the nonlinear inclusion will have the same property. We'll have the Lipschitz continuous single-valued localization. So see, this is a very natural generalization of the classical theorem, where the normal column mapping, when the set C is the entire space, the normal column mapping is just 0. So the linearization, that the linearization has a single, the inverse of the linearization has a single value localization, here means that the this matrix here, this derivative here in the Banach space setting is invertible, and this is the classical implicit function theorem. But now this works if we add also set valued mapping, and this was really a very new idea, which was a real breakthrough in sensitivity analysis. And this particular property, that the linearization has an inverse which has a single value localization, was called by Robinson strong regularity. Later, it was added to this theorem that if the localization has some differentiability property, then this property, differentiability property, also goes into the solution mapping of the nonlinear variation inequality. This is something which I'm not going to go into, but the main thing here is that first we consider a set valued mapping, we consider an inclusion, and we don't claim continuous differentiability of the solution mapping, which is actually what happens in optimization with constraints. Okay, so later it was realized that basically the Robinson theorem works not only for variation inequality, but works for any inclusion of this form here, a function plus a set valued mapping, where the set valued mapping could be anything, could be basically anything. And this property of the linearization of that the inverse has a single valued Lipschitz localization was called strong regularity, and it could be also stated for any set-valued mapping, capital F here, and it is nowadays called strong regularity of the mapping, capital F. This is a regularity property of the mapping F, which is the name has the name strong regularity. Okay, tradition coming from the name of Robinson, and these inclusions here are called nowadays generalized equations. Following again Robinson, who called the variation inequality generalized equations, where we have function depending on the parameter, and which could be nicely differentiable, and a set-valued mapping, and we consider this inclusion here. Okay, so we continue now in a statement of Robinson theorem in more general terms. Namely, this is the most general statement of Robinson theorem I know. Suppose that we have a complete metric space and a linear metric space with a shift invariant matrix. We don't have even a linear structure here in Higgs. P is also a metric space. And then we have a function f, which goes from p to and x to y. And also we have a set value mapping from x to y. And consider this generalized equation here. And I'd like to know what happens with the solution mapping of this generalized equation. And here is the statement. Suppose we have two constants. So this is a play of two constants, kappa and mu, that are positive, and also the product of this constant is less than 1. Remember, less than 1. Then we have another function x, which acts from x to y, such that the value of at x bar is equal to that value here, this is technical. But most importantly, the Ellipses models with respect to x uniformly in P of the difference between f and h is strictly less than mu. Also suppose that it's clear that h is an approximation of f, an approximation of f. And if f is strictly differentiable with respect to x uniformly in P, then h could be just the strict derivative with respect to the strict derivative mapping. Now, for the approximation, we assume that h plus capital F is strongly regular, meaning that the inverse has a Lipschitz continuous single-valued localization. And this localization, the assumption is it has the Lipschitz constant kappa. Kappa is the same as here. So kappa and mu are tied with this condition here. Then the conclusion is that the solution mapping of this general inclusion has a single valued localization, which also has a Lipschitz modulus, which is estimated in this way by the kappa, mu, and the Lipschitz modulus of f with respect to p. So again, we see here kappa mu less than 1. And again, we have in the Hildebrand-Gracie theorem, basically we have a contraction here, and we have to figure out where it is and to apply the contraction mapping principle. But if you don't want to do that, if you don't want to go into contraction, you can use one of the many available proofs of this theorem in the literature, using, for example, Eckert principle, using a Newton method, using other facts from the literature, using metric regularity, something more modern. So this is, but the bottom of the things is this inequality here. So, so there is even more which can be extracted from this theorem. Namely, we can identify how the constant kappa and mu and the constant of the localizations of the linearization and the nonlinear mapping depend on each other. Okay, and here is a theorem which keeps track on the constant. Again, we have a set valued mapping F. And now I'm putting this in the context of the inverse function theorem, not the implicit function theorem, which was in the previous slide. I'm going to talk about the properties of the inverse mapping, which is a particular case. Of course, inverse mapping theorem is a particular case of the implicit function theorem. Basically, they're equivalent. Anyway, so we are now assuming that we have a constant kappa and also this neighborhood. Remember, we have a localization of the graph of the mapping, which means that we have to have some neighborhoods around the reference points. And we assume that this localization now into this truncation of the inverse mapping has a single valued and Lipschitz is single valued and Lipschitz continuous on this in its domain, and it has a Lipschitz constant kappa. Then take any mu such that kappa mu is less than 1, and kappa prime such that this inequality holds, and then for every positive alpha and beta such that this inequality holds, and every function f which satisfies these two conditions, most importantly is Lipschitz continuous with respect to Lipschitz continuous with a Lipschitz constant mu. For every such function, we obtain that this localization of the sum of the f plus capital F inverse is Lipschitz continuous on this truncation with the ball with radius alpha, is Lipschitz continuous on the ball of radius beta with Lipschitz constant kappa prime. It's a kind of looks like a a little bit of a why complicate the picture. So it turns out this is the key to what I'm going to talk about a little bit later. When we start looking at what we actually want to know from this Robinson theorem. Okay, I'll come to this in a minute. Okay, now move to applications. We have a Karush-Kuhn-Tucker mapping here. Consider some regularity of Karush-Kuhn-Tucker mapping. We have a nonlinear programming problem. Everything is very standard. The functions are twice continuously differentiable. We introduce the Lagrange functional in the usual way. And under constraint qualification, we can write down the optimality condition as a generalized equation. Now we as a variation inequality, which is a particular case of a generalized equation. And this is of this form. Here, this is again the normal Kohn mapping. The function f is just composed by the derivatives of the Lagrange Lagrangian with respect to x and y. Y is the Lagrange multiplier vector, and E is this particular case here. So we come to the realm of variation equality, a generalized equation. I would like to, and the solution mapping of this variation equality will be the KKT solution mapping, KKT mapping, the function which realizes the Karush-Kuhn-Tucker pair as a function of the parameter P. Okay, and here is the main theorem, which is, again, belongs to Steve Robinson, who proved it in his 1980 paper. We need some notation here. This is, I is the set of indices with when the nonlinear constraints, when the constraints are active, the inequality constraints are active. The equalities are, of course, always active, and this is the index set y0 where the constraints are active and the Lagrange multipliers is 0, corresponding Lagrange multipliers are 0. This is something which Fiacco and McCormick assumed is empty. This set is empty, and this is the main difference between the Fiacco-McCormick case and the Robinson's case. And then we have this critical subspace, the so-called critical subspace here defined in this way. I'm not going to explaining what is this. This is very standard now. And now here's the theorem, the consequence of Robinson theorem, which is also proved by theorem that yes, if the gradient of the active constraints are linearly independent and the so-called strong secondary condition holds, then the mapping S, the solution mapping of the Karush-Kuntake optimality system, has a Lipschitz continuous single value localization around the reference point. Moreover, it could be proven that if this matrix here has a full rank, then these conditions 1 and 2, this is node 1 and 2, this is A and B, the type here, they are not only sufficient, but also necessary in order to have this thing here. So what is the difference here? The difference is that now, and this is classical thing, that now we get rid of the strict complementarity slackness, and we have the same conditions are in the Fiaco-McCormick theorem. So we have the same situation, but now much stronger result, which doesn't claim continuous differentiability of the solution, but we don't have this continuous differentiability anyway. We don't have differentiability at the point when the constraint change its status. Okay, here is the application to mathematical programming. And now we are coming to optimal control. We consider a standard optimal control problem, minimizing the integral cost subject to a nonlinear state equation and control constraints. So we assume we don't assume the presence of state constraints, just control constraints, which are represented by a convex enclosed set capital U. The usual spaces for control and state are assumed, and P is a parameter. So we're going to consider the strong regularity of the solution mapping of this problem. The standing assumptions are that U is closed and convex. The function phi and G are twice continuously differentiable, and their second derivatives are in Lipschitz continuous locally. And also we have a reference solution X bar U bar for problem with P bar. First are the necessary conditions. Some people call it Pontryagin maximum principle. Actually, it's something much more elementary than the full size Pontryagin principle. The optimality system in this case will be based on the definition of the Hamiltonian here. And we have the state equation in the optimality system. We have the so-called adjoint equation involving the adjoint variable Q. And here is the derivative of the Hamiltonian with respect to X. And we have a variation inequality here, pointwise variation inequality for the derivative with respect to U of the Hamiltonian and the normal con mapping to the set U, which could be also written as a minimum condition for the Hamiltonian, or maximum for the minus Hamiltonian, which goes back to the format of the Pontryagin principle. That's why it's called maximum principle, by the way. And this all, if we put the spaces we need, we put the spaces we need in use in this case could be, of course, written as generalized equation with a parameter P, which, however, in this case is not a variation inequality. For example, because we have to use here the adjoint space of the space of X and U, and this is not clear why should we do that here, and we don't want to use that because it going to the adjoint space to the space of W2 would be fine, but if we take the continuous function for the state, this will be even more complicated. So we don't go into variation inequality here, but we don't have to. We don't have to. Okay, so now we'd like to study the strong regularity of the optimality system, and there are two conditions here which I assume. The first is the so-called coercivity condition, which is basically positive definiteness of the second derivative of the Hamiltonian. And the second one is isolatedness condition, that the optimal control is an isolated solution of the inclusion here, which is the maximum, basically the maximum condition in the Pointryagin principle. It turns out that under coercivity and isolatedness, the optimal control, which is basically L infinity function, can be identified with the Lipschitz continuous function in time. The mapping describing the optimality system is strongly irregular. And also the mapping from P to the set of solutions of the optimality system is Lipschitz continuous. This is the same as we obtained in the for mathematical programming problem, of course, adjusted to the optimal control setting. Well, now we're going a little bit farther. Now we're going to use discrete approximation we're going to use strong regularity in order to study discrete approximation to this problem. Namely, we introduce the Euler scheme here, the classical thing again. We have a discretized interval 0t over the with equally spaced nodes ti, and we take the Euler scheme for the state equation and for the functional. We can write down the optimality system of the discrete time problem in this way again. And it turns out that under coercivity and isolatedness, there's two conditions. We obtain that the solution of the discretization is a good approximation of the optimal solution of the continuous time problem. Namely, we apply all this machinery of Robinson theorem now, but not to study dependence on the parameter, but to study dependence on the quite aggressive change of the model here, going from continuous time to discrete time. And it works nicely, and we can get this condition here. Applying a version of Robinson theorem, we have to, of course, adjust it. And here is the place where we have to keep track on the constants. And this special theorem I presented as a third version of Robinson theorem. Okay, Newton method. So we know the Newton method. Everybody knows this. It also can be applied to generalized equation. It just results in this inclusion here. And optimization, this is called, well known as sequential quadratic programming. In 1979, Josephy, a student of Steve Robinson, proved that the strong regularity implies quadratic convergence to a solution when the starting point is close to it, close to the solution. So there is a quadratic convergence under strong regularity again for the optimality system. And we can add to that more, that in optimal control case, under coercivity and isolatedness, when the Newton optimal control, the Newton method or the SQP is applied to the discretized optimal control problem with a parameter that the convergence of the Newton methods is uniform with respect to the discretization step and small changes of the parameters. Instead of presenting you here a theorem which is very bulky regarding this dependence, I'll give you an example. This is an optimal control problem which models the spacecraft reorientation. This is the system here. I'm not going to go into explaining what is this. Not to mention that I'm not really an expert in aerospace. So, but this is the goal is to stabilize the reorientation of the spacecraft when hanging somewhere in space. Okay, so when you apply the Newton method with different step sizes and different values of the parameters, we get a picture like this. These are the iterations how the error goes to 0 with the number of iterations. And we see that changing the parameters of the problem and changing the discretization step doesn't basically change the way the method converges. We have uniform convergence of the method subject to perturbations of the model and subject to approximation of the model of the optimal control problem with the discretization problem. Okay, there's another problem. There's another result here, which comes down from coercivity, isolatedness, going through strong regularity. That in this case, we can define the so-called optimal feedback control. We can show that there exists a mapping from t to x to the variable u to the control u at t x, such that when applied to the plan, this mapping, when applied in this feedback configuration, then it produces the optimal solution for every initial state. This is the holy grail of control theory, the optimal feedback, the stabilization feedback. And it turned out that strong regularity actually works also here. And most importantly for us in the last several years, it works for model predictive control. This is a new paradigm in control theory, which basically is model predictive control is an algorithmic approximation of the optimal feedback control. I'm not going to go into details here. I'm going to give you this graph only from the number of publications on MPC on model predictive control in the last 30 years. And you see the graph here exponentially. This is thanks to Ilya Kolmanovsky, who gave me this graph. And this, I can tell you that these are mostly engineering papers. As usually, the mathematicians are behind the engineers. And very, very few from these papers here are really papers written by mathematicians. That's really mathematical papers. And there's so many things to do in model predictive control here. Applications are everywhere. They first started with the so-called slow processes because we have to, the people need a more computational power in order to use this paradigm. But also nowadays they apply to the rockets, to the spacecraft, to controlling the much faster processes. So what is the MPC algorithm? So I'm going to be very brief. First, discretize the problem, then use the following iteration. Suppose that you have already found the MPC generated control on the intervals 0 tk. Tk is one of the nodes. And we discretize the optimal control problem in the remaining horizon in the same way as the usually with using the order scheme. And then find the optimal control for this discretized problem and take in the next step, in the next time interval, tk plus, take the constant function uk, which is a solution of this problem, and apply to the continuous time problem. Then measure the resulting state with some error, say k, and go again to the iteration. So this is an algorithmic approximation of the optimal feedback control. Instead of building a device which may not exist, which automatically produces the optimal control, we chop the interval in small intervals. We have a very good computer. We measure the states. We compute very fast the optimal control in the next time interval, and we apply it to the plant. So this is clearly an approximation of the optimal feedback control. Surprisingly enough, till very recently, people, of course, knew very well that this is a good approximation of the optimal feedback control. But there was no mathematical proof of that. And why it is so interesting for mathematicians, because the MPC involves many things that come together here. Involves discrete approximations, involves perturbations, and involves optimization methods. So we have a discrete approximation of the problem, and immediately you have a question. What is the error bound in terms of the step size h? We change all the time the time interval and the initial state. We measure the initial state. What is the dependence of the solution on this initial state? We repeatedly solve similar optimization problems. So the question is, does the method behave similarly through the iterations? Maybe it will break down somewhere in the middle. Why? And do we need always to solve exactly the optimization problems? Could we solve it approximately and then approximate the solution? And finally, the MPC generated control, we get this control finally. What is the difference between the MPC generated control and the optimal feedback control? Apparently, this is an approximation. So what is the error of this approximation? It turns out that we could get answers, at least in particular cases, of these questions if we employ strong regularity. And here is one of the results, which I'd like to just briefly sketch. If we have an optimal feedback control, which is here, you have an XF and you have the MPC generated control, that the norm of the difference between these two things are bounded by the discretization step plus the error we make in measuring state, given in this form. So we have an error estimate how the approximation represented by model predictive control, good it is, how good it is relative to the optimal feedback control. So we know that if this h is small and if the error is small, we can nicely approach the optimal feedback control. Okay, so closing remarks. I think I'm finishing my time here. Is this correct? Have 2-3 minutes more? Okay.
This is correct.
Yeah. So closing remarks. Finding generalized derivatives remains a main goal of sensitivity analysis. But these are not always available, the generalized derivatives. Instead, one may directly employ quantitative properties. In strong regularity could be particularly helpful for determining Lipschitz constant because it simplifies the problem. The Robinson theorem go from nonlinear to linear problem. Also, strong regularity could be used not only to evaluate the effect of parametric perturbation, but also to find error estimates for various approximations of the problems and obtaining also uniform convergence of algorithms. And finally, strong regularity is just one regularity property set by mappings involved in optimization problems. There are several other regularities which are less developed, but not less important, such as metric regularity, subregularity, strong subregularity, semi-regularity, and they're not fully exploited yet. And there is a lot of things to do here, in particular in applications to optimal control, and in particular to applications to model predictive control, which turns out to be a very important approach to controlling in practice. Here are some references. The first is the book with Terry Rockefeller. The second is the book which we can find a lot about regularity properties of mappings appearing in variational analysis. And these are two papers which are very recent papers which are about application of strong regularity to model predictive control. Thank you very much.
Thank you very much for a very nice talk on a very important result in optimization and analysis. Yeah, it's very nice applications, and it impacts a lot also the numerical part of optimization. So it's time for questions. So let me start with a comment by Titar Klatte. Titar, do you like to say something or to read what you wrote in the chat?
No, it's not necessary because it is only a notice. Henry Wolkowitz noticed that sensitivity analysis was done by Tony Fiacco for many, many years. And I wanted to add that in the 80s and 90s, there was every year in May, days before Memorial Day, 2 days meeting in Washington, D.C. For sensitivity analysis. It has nothing to do with Asen's talk, which was, of course, very nice and gives, of course, now the state of the art in today. Thank you very much, Asen, for this talk.
Thank you.
Thank you for a comment. Yeah, so Fiacco was one of the pioneers of this type of results, in particular for optimization. So are there other questions or comments? I'd like to ask a question, Asen. So the Newton scheme for several problems, is there or are there, let's say, some useful implementations, applications of this algorithm? Or is it more a theoretical statement that it gives more this type of understanding?
Well, we used SQP and Newton method for model predictive control, and there are several issues there. In model predictive control, this is the application I've been involved with. Maybe there are other applications, but this is the one I'm. The first one, in model predictive control, we need to solve things fast. Okay, Newton method is quite fast, but it takes time. So now the question is how to make the Newton iteration to be less time consuming, because in model predictive control, we have to compute an optimal solution of a quite involved optimal control problem, optimization problem in discrete time. Only during this time interval of updating the MPC, the model predictive, updating the control. And you could imagine that these are very short very tiny partitions of the seconds, where if you're controlling a satellite, you have to do it very fast. So the Newton method is fine, but the question is, how can we reduce the time of computations getting similar results? And here is one idea: use the Kantorovich approach in order to reduce the time, not to compute the second derivative of the Lagrangian or the first derivative of the function, which is in the equation at each iteration, but to use the first or the every 10th the value of the derivative, to compute the value of the derivative at every 10th iteration, something which will reduce considerably the time. This is one thing. The second thing is, should we really do exact computations? I mean, can we stop before reaching the desired accuracy? Can we stop there? And because in the next iteration, we're going to again approximate something. So can we use approximation to approximate again? So propagation of approximation, this is something which is not quite well solved, for at least to my knowledge. Something to explore. And also the other thing will be, of course, particular realizations of this for particular problems. It turns out, in my opinion, it's very hard to say that we know we have a computer program or method or package which solve everything. I don't believe in such statements.
So actually, probably I posed my question not in the right way. So actually, what I had in mind was the following. So of course, I know that the SQP algorithms are relying on this technique. But what about situations where the operator capital F is not a normal cone, but let's say a maximum order operator? Are there such schemes, or are there such problems which can be solved?
I know what you're talking about. No, my answer is no, and this is something waiting to be explored.
Mm-hmm. Okay.
Something for you're talking about all this projection type methods.
For instance, yes.
Yes. Yeah. This is waiting. This is waiting for young and smart people to.
Okay.
To do it.
Yes. Thank you. Russell has a question.
Yeah. Hi, Asen. Thanks for the nice talk. You mentioned at the very end that metric regularity, metric subregularity, strong metric regularity, I think all of these different notions of regularity at the solutions need to be explored. Can you think of an example where metric regularity is necessary, not sufficient, necessary for achieving a particular kind of convergence result that you would want, some quantitative convergence, where the weaker notions of metric regularity, like subregularity, won't suffice, won't give that to you?
No, the answer is, Russell, thank you for the question. I only recently started to understand that in many cases when I used to use metric regularity, actually metric subregularity is completely sufficient, and perhaps much better. Thank you for the question. I don't know the answer to this question. I don't know an example. Well, I don't know. I cannot generate now on the top of my head, but I know I'm aware of this. That this may happen. In particular, when we have things in optimal control. I'd like to mention the recent work of Vladimir Milov and his group for problems in optimal control that are they do not satisfy the cursivity condition. When we don't have this in a natural way, the strong regularity, then we have to go into strong subregularity. Mm-hmm. And also in order to prove also convergence of the Newton method, you don't have to use metric regularity. And there is a theorem which also says that if we have subregularity, metric subregularity or strong metric subregularity, we have a very similar situation, very similar theorem, a little bit weaker theorem, but yes, it is very quite possible. But this is something which I wish I could have and would have time to explore in the future. But that, yes, this is something which very much is in the front line of the research in this direction.
Well, I've been putting my eggs in the subregularity basket because we were able to show that if you have a method that converges linearly from any starting point in a neighborhood of a limit point. And the operator has other nice properties like firm non-expansiveness or something like this, then metric subregularity must hold at the limit point. So that shows that its subregularity is necessary for linear convergence. But if you require superlinear convergence or something like that, I could imagine you'd need a higher order of regularity like metric regularity, not just subregularity. And then, but I haven't seen anything like that around.
Now I better understand your question. I don't know an answer to that. I just don't know.
Okay, thanks.
I actually, yeah, but yes, I'm really, I really think I'm sure that these regularity properties have a great potential to be applied to algorithms, various kinds, not just the Newton method. I did the Newton method.
Your guys' books convinced me of that. I've been going somebody else talking.
Thank you, Asen. So
Sure.
we have another question. Asen, so actually it's a question in the chat. So Thomas P is asking for the source of the rocket control example.
What? Excuse me, I didn't understand.
So asking for the for a reference of the rocket control example. So you had so this was the example you presented.
Oh, this I have to ask my co-authors.
Okay.
This is the source is Ilya Kubanovsky, of course. We work with him and his group, and I'm really, this is my I'm currently employed, by the way, by the aerospace department of the University of Michigan, and I have all I get from them are various examples which are very interesting, and it's really very exciting to see the things that these theorems we prove that they actually work. They work in practice, and they can be applied for very practical problems which are quite important. And this happens in aerospace engineering, where this is the cutting edge of technology, and lots of applications of optimization and control, lots of applications. Fantastic field of development. Unfortunately, the mathematicians are as usually very slow in going into applications and adapting themselves to applications. And a good example for that is model predictive control.
So the name of the collaborator was Ilya
Kolmanovsky. Yeah, you can find him easily. Just Google him. University of Michigan. Okay.
Thank you. So Asen, I have another question. So the Robinson result, or should we call it Graves theorem, in the very abstract setting of metric spaces? Okay, who proved this result? Is this your result?
Well, this is basically, you know, the whole thing is that, yeah, well, I stated it. Well, who proved it? Well, Robinson gave the idea. The main idea, the main breakthrough was that we don't have to work with equation. It's sufficient to work with inclusions. Mm-hmm. And he showed the way to work with inclusions. And the rest is just, you know, applying this, extending this. It is true that I was probably, but I don't know of anybody else before me, realized that we don't have to consider just variation and quality. There's any inclusion could be done in that. Yeah, and also in very general spaces.
Okay, so it was just net.
But I don't consider this as my quality.
Okay, so thank you. So are there other questions? So then we can stop here. Thank you very much for a very
Thank
nice
you
talk
very much. Thank you, everybody.
on a fantastic topic. Yeah. So many thanks to the audience, and yeah, also for the nice discussion. So I just want to announce that we will post the slides and the video on our website, and that our speaker next week will be Ben Sturmfels, the director at Max Planck Institute in Leipzig, one of the two Max Planck Institutes for mathematics in Germany. So Ben Sturmfels is working on topics related to optimization, but also discrete mathematics, and probabilities, and so on. So I wish you a nice week. Thank you very much, Asen, for a fantastic talk.
Thank you. Thank you very much. Thank you, all of you.
Thank you, everybody.
Bye.
Bye.
Thank you.
Bye. Bye, Radu. Thank you very much.
So Asen, it was fantastic. Yes, we had a great audience, many people. Yeah, I mean,
Good.
yes.
So do you have how many do you?
So we had about 120, yeah, which is great.
Okay.
At the moment, more than 110. Yes, somewhat 150. Yes, sure.
Yes.
Oh, good. Good.
Thank you, Mr. Botts. That's very nice that you organized this seminar.
Thank you for attending. Thank you very much.
Valuable contribution. Thank you.
Thank you. Thank you.
Best.
All
Stay
the best
safe.
to you. You
Safe.
too. All the best. All the best. Thank you.
Okay.
Okay.
Bye,
Asen.
everybody. Bye, Radu. Bye.
So please send me the slides, Asen. Yeah?
Yeah. Sure.
Okay.
I will. Thank you.
Okay.
Bye.
Thank you. See you. Thank you. Bye. We have to talk about something we just planned yet for last summer, but probably should do it in future.
Whenever
there was something planned to do in Vienna for the summer school, yeah? but then
yeah.
Vladimir said that we should postpone it. Yeah, so we can postpone it, of course. Yeah.
Yes, we will.
Yes.
Of course, in the current situation, there is no.
Yes.
Yes.
Okay.
We will. Yeah.
Yes.
Yeah. It's
Okay.
on the plan. Thank
Very
you.
good. Thank you. Bye. Thank you.
Bye.
Thank you.